later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information we will be sharing today. Now, without further ado, I'll pass it on to our presenter so that we may begin.
Hello. Were we going to send the links out for the separation?
The link is in the chat for everyone.
Okay, awesome. All right then. So I think we can start, right?
Yes, ma'am.
All right. So hopefully everyone's doing well. Welcome to another session. I believe this is number 6. And so today we're going to be looking at synthetic division and complex numbers. So at any time, if you have any questions, please feel free to stop us by either raising your hand or putting it in the chat. Okay, so synthetic division is actually going to be a tool that you can use in the next section, starting with 2.5 and so on. And really, this method is to help us identify or find the zeros. That's what we're going to be using it for the most. And although there's other different ways to do it, synthetic division will be able to break down a polynomial. For example, something that is to the 3rd power or higher. And our goal is going to be to use synthetic division to find some zeros, but also it's going to break down the polynomial to something that is quadratic, and then we can use factoring or the quadratic formula or the square root property. So in this case, this is your 0 here. That's what we'll be looking for. And we're going to be using this factor here, x minus 2, quite a bit. Not specifically x minus 2, but x minus some number. And so before we actually go into synthetic division, I wanted to just give you an example on long division, since some of you are doing that this week and it's part of your assignment. And so to do long division, these are the steps that we're going to be taking. And it really works like if you were just dividing two regular numbers. So the first thing you want to do is arrange the numbers in descending powers. Then we're going to divide the first term of the dividend by the first term in the divisor. And I'll explain what all of those terms mean in the actual example. And then we're going to multiply every term in the divisor by the first term in the quotient. And then we're going to be writing that beneath and subtracting. And then we repeat the same cycle. And you know that you can stop once, like you keep doing the cycle, but once the degree of the numerator is less than the degree of the divisor, then we know we can stop. And whatever is left is going to be your remainder. Okay. So there's a lot of steps here, but when you see an actual example, you'll see that it doesn't seem as much with the actual example. So if we wanted to divide this, the first thing you want to do is to make sure that the polynomial is in descending order. So here we have a cube, a squared, then we have a 1, and then we have the constant. And so I want to make sure that I write those in descending order. And then I also want to check my divisor for x minus 3. And it is in order, right? And so the next step is going to be to divide the first term of the dividend. The inside stuff is your dividend by your divisor. So here we have 20x cubed divided by 4x, and that gives us a 5x squared. So we go ahead and write that at the top. And now we're going to multiply 5x squared times 4x is 20x cubed. And then 5x squared times negative 3 is negative 15x squared. And just like if we were doing regular division with two numbers, we're going to subtract whatever we get here. But notice that I put it around parentheses because we're subtracting the entire polynomial here. So once I distribute that negative, then I get negative 20x cubed plus 15x squared. And then we start the process again. So we do the subtraction here. 20x cubed minus 20x cubed is 0. 35x squared plus 15x squared is going to give me a negative 20x squared plus 23x. And then we're going to repeat the process. And by repeating the process, what I mean is we're going to take, let me circle it here, the first number and the first number in the divisor and divide them. So negative 20x squared divided by 4x is going to give us a 5x, right? So negative 5x times 4x is negative 20x squared, and negative 5x times negative 3 is positive 15x. But don't forget, we have to subtract the entire thing, and so I put it in green here. And so when you distribute negative times negative, you get a positive 20x squared, and negative times a 15x will give you a negative 15x. Okay, so that's this line right here. And so we're going to be adding, so negative 20x squared plus 20x squared is 0. 23x minus 15x is 8x. We're going to bring down our next term here, which is negative 6. And then we repeat the same cycle. 8x divided by 4x is going to be a 2. So if we multiply it, 2 times 4x is 8x, and 2 times negative 3 is a negative 6. But remember, since we're subtracting, I'm changing the signs for each of these two terms. So we end up with negative 8x plus 6, and then we subtract, so we end up with 0. Okay, so let's look at what these terms mean. So the answer that you get up here, we call that the quotient, and we're going to be using the quotient quite a bit. The thing that you're dividing by is your divisor. The last thing down here that's left over is your remainder. And the inside of this division here is called the dividend. Okay. So when you're writing your answer, you want to enter the quotient plus the remainder divided by the divisor. So in this case, this polynomial is equal to the quotient plus the remainder divided by the divisor. So when you start doing these problems in 2.5 next week, this is one method that you can use, or you can use synthetic division, which is the topic of today's session, right? So synthetic division is just a shortcut for long division, and you can use synthetic division whenever you have your divisor in the form x minus c. If your divisor is not in that form, you can still rewrite the divisor so that it looks like that form, and then you can still apply synthetic division. So these are all the steps. And again, once we do examples, it'll be a little bit more clear than just reading the statements here. But the first thing, again, is to rewrite this in descending order. And then we're going to identify the coefficients. Remember, the coefficients are the numbers that are in front of the variables. So the A, B, C, and D. And more importantly, you want to use a 0 if you're missing a term. And then we're going to write C. We're going to use C for the divisor. We're going to write that so that we can use the synthetic division. And then all of these steps here, let me just go ahead and show you the example, because it'll be a lot easier once we look at it. So the first step is write your coefficients. So I have my A, B, C, D. And then we need to identify K. So in this case, K is right here. If you had X plus K, then in reality, this would be, your K would actually be a negative K. Okay, so right now we're using just a positive K since it's already in that form that we want it to be. So you're going to write your K on the left-hand side. The first thing you want to do after you do that is we're going to bring the A down. So the A is going to come down. And then you're going to multiply K times A and write it up here. And then we're going to add B plus K times A. So that becomes a B plus K times A. And then you repeat the same process. You're going to take this term here times the k, and then you go write your answer here, and then you're going to add, and then you would put your answer down here, and you do this all the way till you get to the last number here. Okay, so let's do an example. So again, the last number here represents your remainder, and then everything before that is going to be your quotient. Okay, so let's start off by first identifying what k is. So if you take a minute, put down what you think k is in the chat, and then we'll continue from there. So remember that your form has to be x minus some number. So what would k be in this case? Okay, so that's your divisor, right? So your k comes from the divisor, which would be the 1. Okay, so in this case, k is going to be 1. Then we're going to list the coefficients. So your coefficients are 1, 5, and 6. So we write them here. So next, we're going to bring the 1 down. So the 1 will come down here. And then the next step is to multiply 1 times 1, which gives me a 1. So I write it up here. And 5 plus 1 will give me a 6. Okay, and we repeat the same thing again. So 1 times 6 will give us a 6. So we write it up here. And 6 plus 6 will give me a 12. Okay, so we're done. There's no more numbers here. So the last number is your remainder. So that's your remainder. And the numbers before it, we're going to use to get your quotient. Okay, so remember the 156, that's just your dividend, which is this whole thing here. But your quotient is what we're going to be using to help us find the rest of the zeros. So the quotient, you always want to start with 1 degree less. So this polynomial had a degree of 2. So when we write our quotient, we're going to go 1 less. So you're going to start with just 1. So the 1 here would be an x. So here's my x. And then I would have my 6 is my constant. And then my remainder goes on top here as my numerator divided by the divisor. Okay. So this part here, I see students have trouble with that sometimes. So again, the number 1 here is the coefficient of x. To determine the power, you're going to go 1 less. So if you had a 2 here, then this is just a 1. And then this would be 6. But we don't write it this way, right? We can just write x plus 6. So we have a few more examples. That way we can get used to it. So here, the first thing is to identify k, which is 8. Then we're going to write our coefficients, 4, 36, 36, and negative 32. Bring down the 4. And then 8 times 4 would be 32. And then we're going to go ahead and add these two. 36 plus 32 is 68. And then times 8 is 544. Plus 36 is 580. Times 8 is this big number here, right? So our remainder would be 4,608. Now, the remainder is going to be important for us. If you get a remainder of 0, then that's going to make us like super happy. If you don't, then that's a different story, but we'll talk about that later. Okay, so here our remainder is 4,608, and then we're going to use the numbers before these numbers here to get our quotient. So we're going to have the 4. Remember the degree here was a 3, so I'm going to go 1 less, so that would be a squared. And then after x squared would be an x, and then you have the 580. Okay, so that's what I have here. That's your quotient. Okay, any questions on that one? Okay, let's look at the next example. So I'll give you about 30 seconds to figure out what your k is going to be in this example. 7, 7. Okay, so almost 7, right? So remember, keep in mind that your k has to be written in this form. And so your x plus 7, we can write it as x minus a negative 7. So we can see now that our k is going to be negative 7. Okay, so you want to think of it as k is going to be the opposite of what you see here. So if you have a minus, then you'll use a positive. If you have a positive, then you'll use a minus. Okay, so thank you for trying the answers there. So this is just what I wrote earlier. So k is going to be your negative 7. And so then here, what are we going to have here? We're going to have our coefficients. And so our first number will be what? So our first number would be a 3. And what would be our next number? So the first thing I had to do is notice that we had 3x cubed minus 6x plus 21x squared and so on. And so these are not in order, so I have to first put them in order, which I did here. And so we're going to have our coefficients would be a 3, 21, negative 6, and negative 42. So we bring down our 3. Negative 7 times 3 is negative 21. And 21 plus negative 21 is 0. 0 times negative 7 is 0. Negative 6 plus 0, negative 6 times negative 7 is a positive 42. And negative 42 plus 42 is a 0. So Ruben, what kind of emoji do we get when we have a 0? Yeah, so this is going to make us very happy, and you'll see why in a little bit, okay? So next step is get our quotient. So our quotient, we're going to have the 3. And we know it's an x, but we need to figure out the degree. Since the degree was 3 up here, then we start with a 2. And then 0 would be 0 times x, and then minus 6. But we don't write down we don't need to include that 0x, right? Because 0 times x is just 0. So we can just write it as 3x squared minus 6. Since our remainder was 0, divided by this would still be 0. Okay, there's, I think, one more. Let's see. So here my k is going to be the 5. And then our coefficients, we're going to have a 1, a negative 3. But notice that we don't have an x. So I need to make sure I use a 0. So my coefficients would be 1, negative 3, 0, and 6. Okay. Bring down the 1. 1 times 5 is 5. 5 plus negative 3 is a 2. 5 times 2 is 10. 10 plus 0 is 10. Times 5 is 50. Plus 6, 56. Yes, correct. So if you see a negative number here, then you would use a positive here. If it was a positive here, then you would use the negative. So the quotient is going to be x squared plus 2x plus 10. And then your remainder is 56 divided by x minus 5. So a remainder is not a good thing for us. And again, you'll see why in a little bit. Like, why is it important to get a remainder of 0? Not that it's bad, but it just makes us try different methods. Okay. Another thing that you're going to be asked to do is to use the remainder theorem. And so all this is saying is if you have a polynomial and you divide it by x minus k, so remember that's this right here. What it's saying is that the remainder is going to be r equals f of k. And so let me just put that into terms here. If I put this 1 in here, then notice what's going to happen. So we had f of 1, we know that x is equal to 1. And to find k, we can subtract the 1, so we would have this form here. So if I did synthetic division, I would have my 1 here, bring down my 2. 1 times 2 is 2. 2 plus 0 is 2. 2 times 1 is 2. Plus negative 7, negative 5 times 1. Negative 5, we get negative 3. So that's our remainder. But notice what happens now. Okay, so let me go here. If we use the remainder theorem, and if I want to find what f of 1 is, if I plug in the 1 for all my x's and I simplify, then I get 2 minus 7 plus 2 gives me negative 3. And so notice that this negative 3 and this negative 3 are the same. And so the remainder theorem is just a short way of finding your remainder instead of using the synthetic division. I personally still like synthetic division, but if the question said what is the remainder, then you would have these two options in finding the remainder. So you can either plug in the 1 for all the x's, or you can use synthetic division. Excuse me. And then negative 2, same thing. If we do synthetic division, we get a 0. If we use the remainder theorem, then we get 0 as well. Now, if you get a remainder of 0, as Mr. Carizales put in his in the chat, that's make us very happy. Okay, and the reason is because if we were to graph this, then we know that at x equals negative 2, this number is going to be a 0 of the polynomial. Okay, and in order to graph, we need to find all the zeros. And so these methods would be able to help us to find these zeros. And I'll give you an example. I think it's the next one here. So how does synthetic division help us solve equations? So if it says find the zeros for the given function, okay? And I'm going to say here, let me add really quick the rest of the instructions here. Given that x equals negative 2 is a 0. Okay, so that's important there, is that they tell us that x equals negative 2 is a 0. Now later in 2.5, and you're not going to need to know a 0, we'll be able to just figure out where to start. But for now, let's just say that they tell us that x equals negative 2 is a 0. Since they tell you that this is a 0, then we're going to use the negative 2, that would be our k, and we're going to write it in here. Okay. So remember, why is that our k? If I bring the negative 2 on this side, I would get x plus 2. And if I rewrite it with the negative, then you can see the negative here. Since they tell me that it's a 0, then once we do synthetic division, we better end up with a 0 here. If you do the work and you don't end up with a 0, then that means that maybe there's a mistake somewhere. Okay. So if we bring down the 2, we get negative 2 times 2 is negative 4, plus 0 is negative 4, times negative 2 is 8, plus a negative 7 is 1, times a negative 2 is negative 2. So we get the 0, so that's going to make us happy. And this is the beauty of the synthetic division here. Your next step would be to get your quotient, okay? So your quotient is going to be coming from these three numbers. So we get 2x squared minus 4x plus 1. So I know I said that's where the beauty comes in. So where's the beauty part, right? Well, the beautiful part is that if you look at the exponent, now you have a square, okay? And so if you have something that's quadratic, then we have easier ways to solve it. We can factor. We can use the square root property if it's available or if it's in the format, or we can use the quadratic formula. So we would take our quotient, right here is my quotient, set it equal to 0. I always like to try and factor, but if it doesn't factor, then you can use the quadratic formula. This is going to factor, okay? Sorry. So this is going to factor, and then we get 2x minus 1 equals 0, and 2x minus 1 equals 0. So we get x equals a half and x equals a half. And so this is 1, 0 here, this is 1, 0 here, and then the third 0 is the one that gave us this remainder of 0. So notice that the degree is 3, so that means we should have 3 zeros, which are -2, a half, and a half. So since these are repeated, then that also tells us something about the graph, right? Whether it's going to touch or cross or anything like that. And so since it's repeated an even number of times, then it's going to touch. Okay. So again, it would be a lot harder to set this equal to 0. And try to solve this. But if you use synthetic division, break it down to a quadratic, then it makes it easier for us because of the methods that we already know how to use. Okay. So right now, this example is kind of like an introduction. Next week, when you start doing your 2.5 section, then you're going to get into deep on how to find the zeros. And so it's kind of exciting because you end up with like polynomials with degree 5, for example. Okay, so we have something to look forward to next week, right? For now, they just want you to be familiar with the process. Okay, is there any questions on synthetic division? Okay, so we have complex numbers. This is from section 2.4. Okay, so section 2.4 wants to talk about us to cover complex numbers. And basically what happened is back in the days when the mathematicians were trying to solve an equation that looked like this, they did all the work, but then when they got to this part, they were like stuck, right? Like, okay, well, what do we do here? And so they created a whole brand new number system, and they called it the complex numbers. And they used that so that they could continue to work on their problems. And this complex number system had to you still had to be able to add and subtract and divide like our normal number system. And so here, if you take the square root, then we say that there's no real solution. Okay, but starting in this section, we are going to be looking at imaginary solutions. So what happens is if you graph this equation, x squared plus 1, your graph is over here on the top. So when we say that there's no real solution, what that means is that the graph is never going to cross the x-axis. Okay. So if you have a graph and I ask you what the real solutions are, if it's not crossing this x-axis, then it means that it has no zeros. So instead, it's going to have an imaginary solution. And so from now on, whenever you see the square root of -1, that is equal to I, okay, where I squared is equal to -1. The standard form, when you're doing your homework, it says enter your answers in standard form. So this is the standard form, A plus BI, where A is the real part and BI is the imaginary part. Okay, so you have to be able to add, subtract, multiply, and so that's what we're going to do here. Okay, so we don't use no more, does not exist, right? Now we're going to have imaginary numbers. So to add A plus BI and C plus DI, we have this here. We add the real parts, A plus C, and then we add the imaginary parts, okay? And then for subtraction, we do the same thing. So let me go on to the examples here. So if we have 3 plus I, plus 6 plus 5i. I have two methods, so I'll show you both because I think the second method is comes more natural than the first method. I feel like the first method here you have to memorize, okay, what do I add first and stuff like that. But if we go with the definition here, we would add the real parts, so that's the 3 and the 6, 3 plus 6, and then the imaginary parts, which is a 1 because there's a 1 in front of the I, plus the 5, and so we end up with 9 plus 6i. Okay. But the second method, the reason I say it comes more natural is because we've been doing this with other variables like x and y and so on. And so I just like to say it's like combining like terms. So you have 3 plus I plus 6 plus 5i. So like terms here would be your 3 and the 6. That's a 9. The I and the 5i are like terms, so we get our 6i. Subtraction. Same thing here. We subtract the real parts. 3 minus 2 is 1. Negative 1 minus 1 is 0i, so we get a 1. If you use just combining like terms, then distributing the negative in here, so we end up with 3 minus I minus 2. Negative negative is a positive. Combine your like terms. 3 minus 2 is a 1. Negative I plus I is 0. Okay. Perform the operations and write the result in standard form. So the first thing you want to do here is to maybe we're going to be adding all this, right? So all I did here is I just dropped these parentheses. Okay. And so that's what I have here. I just dropped the parentheses. But I'm going to take care of this negative 8. Okay. And so do you agree that negative 8 is the same thing as negative 1 times 8? So that's the same thing, right? And then negative 56 is the same as negative 1 times 56. So you might be asking, well, why are you doing that? Well, in the definition, remember that it told us that I squared is equal to negative 1. So notice what I'm going to do here. I'm going to have, let me just circle some things, that way you can see what I did here. I'm going to add negative 3 plus 5. That gives me the 2. Okay. And then for my negative 1 right here, I'm going to replace it with this I squared. And this negative 1, I'm going to replace it with an I squared. Okay, so you're probably wondering, okay, but why, right? Well, this part here, I can rewrite as I squared times the square root of 8. Okay, and so what happens with the power of 2 and the square root? They become 1, right? Or some of us like to say they cancel. Oops, I went a little too fast here. So let me just rewrite it. So I squared times square root of 8. So the square root and the 2 cancel. That becomes an I. And so that's how we end up with I square root of 8. And then the I squared comes out as an I, and we get 56. Okay. Next, in order to add the radicals here, they have to have the same radicand, which means they have to have the same number inside in order to combine them. So the 8 we can simplify as 4 times 2. And the 56, well, since I'm using, well, we can write it as 4 times 14, but I could have used a different number here. So we're going to have 2. The square root of 4 comes out as a 2, but I already have my I there, square root of 2. And then this 4 comes out as a 2, and then we have square root of 14. Well, the 2 and the 14, there's no way for us to simplify it. So our answer is just going to stay as this, but remember, you have to write it as standard form. So what was the standard form? Let me write it here. A plus bi. And so notice that they both have that I in common. So we can factor out an I, so leaving us with this here. Okay. Ruben, do you want to do the rest of these?
Of
I need to
course.
get some water.
Yeah, no worries. All right, thank you. So now the next thing that we want to also look at is multiplying two complex numbers. Again, in the computer, they might give it to us in standard form, but just keep in mind that the computer always wants us to give the answers in standard form, and it's always the real part first and then the imaginary. So on this particular case, we are multiplying the complex number 1 plus I times the complex number, which is 8 minus 7I. So just like before, treat the I as one of the variables that we've been seeing in the past. Let's go ahead and do FOIL, yes? So again, we're going to multiply this number by both of these terms, and then we're going to multiply I times both of these terms. So let's go ahead and do that. So when I do that, 1 times 8 gives me the 8. 1 times a negative 7I gives me the negative 7I. Now this term, I times 8 gives me plus 8I, and a positive I times a negative 7I gives me a negative 7I squared. So before I can combine my like terms, let me go ahead and I can simplify this guy, the I squared. I know that the I squared equals negative 1. So I'll put it here, negative 7 times the negative 1. Now I do apologize. I went ahead and combined these two like terms. I had two like terms. I have a negative 7I and a plus 8I. When I add these, I have a positive I. Again, I have this still the constant a that had a lonely term. Let's go ahead and do our multiplication. So negative 7 times a negative 1 is a positive 7. Now I have two like terms which are constants. I have the 8 and the 7. So 8 plus 7 is 15, and then my I. And again, this is standard form. My real part is first, and then my imaginary second. Okay? Questions? Easy stuff, right? All right, let's do another example. Let's go ahead and do this one. Perform the operation. This one, we're not doing FOIL. This one is straightforward. We're going to distribute our 17i to the 1 and the 17i to the negative 7i. Yeah, so when we do that, 17i times 1 is 17i, and the 17i times the negative 7i is going to give me a negative 119i squared. Again, we know that I squared is equal to negative 1. So let's go ahead and replace that. So we have negative 119 times the negative 1. That's going to give me a positive 119. And I'm done. I can't simplify anymore. But again, do you see how my answer was like this? Let's not put this answer just like this on the computer. The computer will want the standard form. So when we write it, we want to write the real part first and then the imaginary. So this is the computer it's going to like it, it's going to mark correct. Okay, this one's going to mark it wrong. Even though our numbers are right, it doesn't like the order. It wants it this way, 119 plus 17i. Okay, questions? Awesome. All right. Oh, yes, go ahead, Jacqueline. What's your question? You can unmute yourself if you want. Why wouldn't it be 18i? Okay, so let's back up a little bit. I'm not sure exactly where you're asking me, but so the first thing I have is a 17i, and I'm multiplying. So 17i times 1 is a 17i here. 17i times a negative 7i gives me the negative 119i squared. So where were you thinking the 18i? Okay, no worries, no worries. Again, there's never a wrong question, okay? You guys ask, because this is how we learn. When we get something wrong, but then it's cleared up, it's like we see the light, right? So this is great learning. So no, always keep on asking. So thank you for asking. All right, so let's go ahead and, yes, Yvette, right? We love questions, we do. All right, so again, we've done adding, subtracting, multiplying. What comes next? Of course, dividing, right? So on this one we have we want to write the quotient in standard form, right? So here, okay, we have our numerator and our denominator. So in standard form, what we have to do is we have to identify the conjugate of the denominator. Now, very easy, okay? The conjugate of the denominator is just the same real part and the same numeric imaginary part, except what we're going to be changing is the symbol that separates both of them, okay? And that's how we'll find our conjugate. So first, our conjugate or our denominator is 5 minus 6i. So its conjugate is the opposite of this, which is just 5 plus 6i. Again, we're not changing the sign of the 5, okay? And we're not really changing the sign of the 6i. It's basically the operation that's being separated by both of them, okay? So in case that this was a plus, then the conjugate would have been a minus, okay? But we'll do some more examples of this. So first, we identify our conjugate. Our conjugate for the denominator on this particular problem is 5 plus 6i. So the next thing we have to do is we have to multiply both the numerator and denominator by the conjugate. And we do this because we're multiplying by 1. We just don't want to do one thing to one thing and not the other. And by doing it to both, it's like we're not changing the numbers. We're just changing the appearance by multiplying by 1. Okay, so let's go ahead and do this. We're going to multiply 5 minus 6i times 5 plus 6i. Now there's some signs to this and you're going to see why we do this. Okay, so let's go ahead and multiply this out. Okay, so the numerator is easy, right? We're just distributing the 3 times the 5, the 3 times the 6i, right, which is written here. And then we have a FOIL again, right? We have a 5 minus 6i times 5 plus 6i. So again, the top was very easy. We have 3 times 5 is 15, 3 times 6 is the 18i, okay? And then the bottom, again, after doing FOIL, we have 25 plus 30i minus 30i minus 36i. So let's combine the like terms at what we've been doing before. So we see that the 30i minus 30i, that's going to give me 0. And then it's going to leave me with this, 25 minus 36i squared. Oh, but I know what I squared means. I squared is just -1. So let's go ahead and replace that. Okay. So we have a negative 36 times a -1. That's going to give me a positive 36. And 25 plus 36, that's going to give me 61. Now, the reason why we wanted to multiply by the conjugate is because by us doing that, we get rid of the imaginary part. Okay, yes. So we want to always use our parentheses to indicate, that we're multiplying the whole thing and not just a portion of it. Okay, so thank you, Kim. All right, so again, we did this so we can get rid of the imaginary part on the bottom. And by us doing that, we can apply what we know about fractions. When we have two terms on the top being divided by a common denominator, right, we can separate these two fractions into each own common denominator, right? So 15 plus 60 over 61 plus 18 over 61i. And again, now it's in standard form. We have a real part plus an imaginary part. And again, if I would add these two, again, I would get back this, the 15 plus 18i over 61. Okay, questions? All right, so let's look at now writing complex numbers in standard form. So on this one here, we look at it first and we think, this has nothing in common. How can we add these two things together? But let's go ahead and simplify these problems. So the first thing that we want to do is let's separate this to have the negative by itself, right? The -1, because we know that the square root of -1, that's going to give us that imaginary value, that I, right? So we first rewrite each of the square roots into a product that gives us the negative number. So the first one, the square root of -75 can be written as -1 times 75 plus the square root of -1 times 12, okay? Again, I know that the -1 is also I squared, right, for both. But when we simplify those, we can get I times the square root of 75 plus I the square root of 12. Okay, but we want to also simplify what's inside the radical. Okay, now here what we did it is we can do it with products. Okay, the 75 I can divide it by 5, right, or by 25. I have 3/4, right, so 25 times 3. The 12 I can do the same, right, 4 times 3, right, and we picked the 3 because we see that we're going to be able to get a 3 on both radicals. So when I take the square root of 25, that's 5, and when I take the square root of 4, I know that's 2. So this is going to give me 5i square root of 3 plus 2i square root of 3. Now, we see that we both have now the 2 simplified, right? And with the same radicals, right? So because we have the same radicals, we can combine the outside, right? We have 5i plus 2i is going to give me 7i square roots of 3. So again, we were able to combine these because we had the same radical. And the radical is kind of like the representation we're dealing with x's. Two of these terms have the same variable attached, so we're able to add them. Okay. Questions on this one? All right. So again, we got to be careful because the computer will always ask us to write it in standard form. Now in this one, we just have an imaginary part. So what the computer is going to want us to write is 0 for the imaginary plus the imaginary part, which is 7i square roots of 3. Okay. Now, questions? Okay. All right. Now, let's go ahead and use for practice purposes. Okay, now that I had put on the chat that sometimes or in chapter 1, right, when we got the square root, when we're using the quadratic or solving and we got a radical with a negative inside, we would put as does not exist, right? Well, we no longer can do that. And here's an example of a problem, right? So we have this quadratic equation, x squared minus 2x plus 2. And let's go ahead and use the quadratic equation to try to solve for it. So my a value is 1, my b value is -2, my c value is 2. So let's plug it into our formula. Okay, so here we plugged our variables, our numbers into our variables. Excuse me. And then we simplified. We have 2 plus or minus the square root of 4 minus 8 over 2. And then, we have 2 plus or minus the square root of -4 over 2. And again, in the past, we would just say, the answer does not exist because we would get an error on our calculator. We can't evaluate the square root of -4, but now we can algebraically, right? We know that the square root of -4 can be rewritten as we've done before, -1 times a +4, and we know that this is going to give us an I, right? The square root of -1 is a value for I, so it's got 2 plus or minus I square roots of 4 over 2, okay? Now, they want us to write the answers in standard form, right? So we do the same thing that we had done before, right? Sorry, I'm getting ahead of myself. Let's simplify. The square root of 4 is 2, so we have 2 plus or minus 2i. We can simplify this even further. Let's factor out a 2 from the numerator, okay? Again, I'm trying to get ahead of myself. Let's just separate them. So putting them in standard form is the 2 over the 2 plus or minus the 2i over the 2, okay? So 2 divided by 2, that's going to give me 1. And the 2 divided by 2, that's going to give me 1. It's going to give me the I, right? So in standard form, it's the 1 plus I and the 1 minus I, okay? So now we no longer can say that the answers do not exist. Now whenever we get a negative number in the square root when we're solving problems in this section, we know that our answers can now have this complex number. And again, complex number means that we have an imaginary part. Okay? Questions? All right, and I think we have, again, just our answer as 1 plus I and x equals 1 minus I. Now, since I still have a few more minutes, I want to go back to a problem here that we did, and I'd like to show you something that I do in one of my classes that my students like. When sometimes we can't see the number that is being multiplied by in order for us to simplify. Oops, I think I went too far. Or let's look at this one, right? Let's say that I wanted to simplify the square root of 56 or here, right? I was going to end up with a square root of 56. And we don't have a calculator, or we want to simplify that 56. So what I show my students in class sometimes is to go old school and do a factor tree for 56, to see how I can simplify this radical. Now, when we're talking about square roots, square roots is all about pairs of numbers. For instance, when I ask students, what's the square root of 4? Most of them, the majority, right, answer right away. Oh, the answer is 2. So, but why is it 2? Because square root of 4 can be written as 2 times 2 is a pair of 2's. So that's what comes out of the radical, leaving you nothing inside the radical, and the answer is 2. So it's all about making pairs of numbers, right? So what I do is I get this 56 and I do what's called a prime factorization tree, or a binary tree, where I'm going to simplify this into the building blocks of 56, right? So since 56 is an even number, I'm going to divide by its first prime even number, which is 2. So I'll divide 2 into 56. So I'll say 2 goes into 5 2 times, remainder 1. 2 will go into 16 8 times, right? So, and I got a 28. Then I'll do it again. 2 is a prime number already, but 28 is not. And it's still an even number, so I'll still divide again by 2. 2 will go into 2 one time, remainder 0. 2 will go into 8 4 times, okay? Then I'll do it again. Oh, 2 is already a prime, but 14 is not a prime. 14 I can divide by 2 again. 2 divided by 14 will be 7, right? So the building blocks of 56 are all these leaves that I have from my tree. I have 1, 2, another 2, another 2, and a 7, right? So 56, the product could be written as 2 times 2 times 2 times 7, right? And if I put this under my radical, okay, so again, the square root of 56, I can rewrite it as 2 times 2 times 2 times 7, okay? And again, square roots is all about making pairs of numbers. So I see that I have a pair of 2's that can come out of the radical, and I'll write a 2. And what's left over, I have no more pairs, so I have no choice but multiplying these two numbers again, which is the square root of 14, okay? Which is what we had gotten when we were doing the problems, right? When again, we automatically told you, oh, 4 times 14 because we saw the math. But what if you didn't see it? One quick way to do it, or to simplify radicals, is to go old school, right? To do this factor tree, especially with large numbers too. The computer's going to give you large numbers where you'll say to yourself, where do I begin, right? And that's a good way to simplify your radicals. If you're ever in a bind, just do your old-fashioned factor tree. So does anybody have any questions? Ms. Chuka, would you like to add anything? Okay. All right, guys. Well, thank you for joining us. It was a great hour again. Go
Hey,
ahead, Mr.
sorry, I had my mic muted, but I just wanted to say I didn't have anything to add except that just that next week we're gonna be looking for the zeros and graphing these polynomials. So come out and join us and have a great weekend.
Okay, thank you, Ms. Chuka. Thank you, Mr. Carizales, for today's presentation. And don't forget to sign in. The sign-in link is in chat. And next week, we'd be discussing finding the zeros of polynomial functions for Math 1314. We hope to see you then. And if you do have any questions, please type them in chat. If you need tutoring, we have tutors available.